So hi guys, you're welcome again to another wonderful video of mine. And this is the last video concept on thermodynamics and process. So we are going to be talking about lots and lots of things in this video, which I believe it is more important for most of our advanced students, that is those doing the A-level physics program course, and for the ordinary level students you are supposed to know just some of these few concepts, as the detailed explanation is not needed. But for the JUPEP A-level students and the IJMB students, they are to know almost everything under this chapter. So I don't want to skip it because it is there in the syllabus, and question level they are not that much, but we need to understand this, most especially when you get to universities. Most of these things are going to be treated. As I said, the channel is for different physics students. So I'm going to get started now, and we are going to talk on the first process we call the zeroth law of thermodynamics, as well as the first law of thermodynamics, which I believe we might have studied in the junior classes. It's going to be a long video. I'm going to be very fast because I have to cover everything. Like I said, derivation will be a little bit limited, but in some cases it is needed. So I'm still going to do them. So we start with the zeroth law. So explanation is very important. And when we talk about the zeroth law of thermodynamics, the bodies is just stating that the law is stating that when two bodies A and B are in thermal equilibrium. So let's just keep a note. When bodies, we are talking A and B, are in thermal equilibrium, when A and B are in thermal equilibrium, when bodies A and B are in thermal equilibrium with another body B and C, which is also in thermal equilibrium. And it means, like I said, which is also in thermal equilibrium. Therefore, A and C will also be in thermal equilibrium. Now, the most important thing for me making video for you guys is writing at everything, and which is one of the most important things. So what I'm saying here, guys, is that when you have two bodies which are in thermal equilibrium, there's the amount of temperature flowing in both of them are equal. They come in contact with another body, which are also in thermal equilibrium. When they are in contact with each other, so the body will, they're also going to be exist what a kind of thermal equilibrium between the third what bodies, which is A and C. So that is what the law is talking about, and this is the definition we give to zeroth law. So basically, in chemistry, we define this as a situation, a kind of thermal equilibrium that exists between two or more bodies when they are in contact. I think that is a fast way of definition, which is also good. So that is what we call the zeroth law of thermodynamics. So you can always keep that at the back of your mind. So this is the zeroth law. It's just the law of thermal equilibrium. So that is the definition we give to zeroth law. Two bodies in contact with another, which are in thermal equilibrium, we exist when their body come in contact. The third body between them will also be in thermal equilibrium. So that is what we are saying. A very good illustration. Maybe I should do that. I told you I have a long way to go in this video. So details explanation is also needed for understanding sake and for the sake of those of us that are in A-level classes. So now, if we talk about that, what we are trying to say there is that maybe we make a rule first. As I said, long way to go, dear student. So we We can take an illustration just to understand that. We have two bodies. This is seriously hanging, and this is not supposed to be it. So let's say we have a body A, B, and C. That is, this is body A and B. I'm going to change the color of the marker now. This is A and B. Is in contact with another body. This is the body B and C. They are in contact. And because they are in contact with each other, sorry. So if A and B are in thermal equilibrium and they are in contact with each other, what this is telling you is that what B and C is also in contact with A and B. Diagram not drawn to scale. Just trying to make something out of nothing. No time for all this anyway. Just for understanding, say this is C, point of contact there, that's C. So if A and B are in thermal equilibrium, you can see they come in contact with what? A and B come in contact with B and C. So definitely this is also going to be in thermal equilibrium. So thermal equilibrium exists here. So because of thermal equilibrium that is existing between A and B and C, A and C are also going to be in thermal equilibrium. So that's just the interpretation of that. Then we move to the first law. About the first law, which is called law of conservation of energy in chemistry, which I believe most of you have studied in junior classes. So about the first law of thermodynamics, I'll write that as first law now. That is just what I believe we have studied in junior classes. Conservation of energy. Energy can neither be created nor destroyed. So we can just write what it's, the law is just about conservation of energy. It's talking about conservation of energy for gaseous system. For gaseous system, when it is supplied, when it is supplied or rejected by the body. So what we are trying to say here, because we are doing it in physics way, is for us to understand that the first law of thermodynamics is law of conservation of energy for gaseous system. So we are analyzing a gaseous system. We are not talking about solids and liquids, so we have to keep that at the back of our mind. And because we are talking about gaseous system, energy that is being conserved when you supply it to the body. So when we analyze the first law of thermodynamics, we use what we consider three parameters. So three parameters are considered when analyzing first law. So if you are stating the law, energy can neither be created nor destroyed, it is acceptable, but it can be transformed from one point to another. So analyzing it, when it is supplied to a body, we consider three parameters for first law. We use what we call the heat supply to the body, which is very important to keep in mind. The second parameter we talk about is the internal energy. And the last thing we talk about when we're talking about the first law of thermodynamics is the work done by the system. So these three parameters are very important to keep in mind. And this is how we form our first equation of first law of thermodynamics, which I think is popular for all levels of students to understand. So we say the heat supplied by the body is denoted by the Q, because heat is changing. It can either be upwards supplied to the body if the body can accept it, and body can also reject it. So when it is supplied to the body, it is there will be a change in internal energy of the body. Internal energy will represent by the U. We've talked about that from the kinetic theory of gas. And the work done by the system will denote by what? Change in work done, we take it as dW. What I'm just saying is that the heat supplied to the body is changing. As a result of that, there is a change in internal energy of the gaseous substance. And because there's a change in internal energy of the gaseous substance, the work is being done by the system. So if we have a gas or a gaseous system, if you supply amount of quantity of heat to the body, Then because heat is supplied to the body, so work is done. Internal energy, the body actually has what the internal energy inside this gas is going to be increasing. I'll just write that as the U. That is my explanation. And because that has happened, there will be what amount of work will be done to the surrounding. So by conservation of energy. So by conservation of energy, we're talking about, we write the first law of this one by writing it as the amount, the change in what, the amount of heat supplied to a body makes what, increase what, the amount of what internal energy of the gaseous system in which the heat was supplied. And because of that, work is done to the surrounding by conservation of energy. We have dW. This equation I've written here is now called the differential form of the first law of thermodynamics. I'll write as F-L-T phenomenon. So now, but basically in junior classes, we write the state form of thermodynamics. So writing it in the state form of thermodynamics, equations from understanding of what we've talked about. Energy can neither be created nor destroyed. So we say some quantity of heat is supplied to a body, or that is a gaseous body. Then work is done by the body. When it is supplied to the body stores the gas starts moving. Work is done when distance is covered. And because work is done, there is a change in internal energy we write as T. So this particular equation, I want you guys to keep that back in mind. For now, it is very important for all level students. This is the state form or the equation or formula that is used to solve a lot of numericals in your junior classes. So the state form, which is the normal form, is like heat is supplied, work is done, which cause a change in internal energy of the body. So this is the interpretation we give to the first law of thermodynamics, which we call the state form. This is the differential form, which we are still going to be needed in future as we move forward in the study of thermodynamic process. So like I said, thermodynamic process involves 3 parameters. So we are going to be considering each of these parameters, which I think is very important for every one of us to keep at the back of our minds. Time is not always on our side, but whether we like it or not, we are going to talk about all these parameters one by one. So like I said, we need to understand what each of these parameters stands for. Heat supplied to the body, internal energy, then work done by the system. So under our kinetic theory of gas, we need to understand, we start with the first one, which I think we need to get very well. So we say generally interpretation, a quick one. I will not be deriving too much, but it is important. You watch this video to the end. That is one of those things I used to say. So we say the quantity of heat supplied to a body is given by the formula NC change in temperature. Remember when we did calorimetry, NC is a C, excuse me, it is handy. When we did calorimetry, we say the quantity of heat supplied to a body to raise the temperature by unit mass is given as MC theta. So in this one, we are talking about NC change in temperature. Now, we are talking about gaseous system. When we talk about thermodynamic process, we need to understand that this thing is angular. That is why I'm slowing down a little bit. So NC change in temperature is the quantity of heat required. We say the quantity of heat required to raise 1 mole of a substance. So note that. Now, C here, definition is very important. It's called molar specific heat of a gas. Molar specific heat. That is what we call C. So the quantity of heat required or supplied or rejected by a body, the supply or rejected by a body is given as NC change in temperature. Remember MC theta in your calorimetry. Keep this in mind because it's very important. So this NCV, a quantity of it is now measured, I'll also help you write, in joules per mole per Kelvin, which is also very important. So the first note now, so we said C is just the molar specific of a gas. So that is heat, the amount of this one, I said the amount of heat that is supplied towards n mole of gas. N stands for numbers of mole. In terms of calorimetry, we say MC theta. MC change in temperature, NC change. So molar specific C in that calorimetry is not molar specific heat of gas. So molar specific heat, that one is specific heat of a substance, which I tell you depends on other parameters. But under the topic, we didn't talk a lot about it. Like I said, we have a lot of things to talk about. So the molar specific heat of a gas is noted by C. So now you need to understand that the molar specific heat of a gas is not constant, just like specific heat capacity of a substance we talk about in calorimetry. So you keep this in mind. The molar specific of a gas is not constant. In that calorimetry heat, we talk about specific heat capacity, which is constant. I told you it depends on other factor, but which is not needed in your syllabus as at that time. So the molar specific of a gas now depends on what? A lot of factors. So, and because of that, we can have variable value of what? C. So for variable value of C for when C is variable, just put it in quote, we say the quantity of heat supplied to the body is now, I told you whenever something is varying in physics, we use integration. That is NC, you can say change in temperature, and so just write as dt now. So we take the temperature value that is changing from T1 to T2. So that is if the equation is given in terms of variable values. So these are just the cases which I think all students need to keep at the back of their mind for now. And again, I've told you, whenever I highlight a point, definitely that point is very important for students to write it in their notes. So you keep it at the back of your mind, and you write this note to the end. Watch this video to the end because you need it. So the first parameter we call heat supply is given in terms of what? As you can see, NC the temperature. We take the second parameter we call internal energy of the gas. Now, about internal energy of the gas, I won't talk too much about that because we have talked about that before under kinetic theory of gas. Please watch our video with respect to what? The playlist. So internal energy is the second factor. So the internal energy, which we call the U, or U basically, because I'm using the first law which I gave to you, which is Q is equals to heat is supplied to the body. Then there will be some kind of work done by the body. Because of that, there will be a change in internal energy. We've talked about Q, then C, change in temperature, which can also be variable value of C. That is integration of NC change in temperature, dt, taking the limit of T from T1 to T2. Now, we move to internal energy. And for internal energy, we've talked about that before. Like I said, remember that kinetic theory of gas is given as F by 2, where F stands for degree of freedom, nRT. Keep it in mind, very important, because we know internal energy is the measure of what? Temperature, which is proportional to temperature. So U equals to F by 2 nRT is not the first time of you guys hearing this one. So the U change in the internal energy will now be F by 2 nR dt. So when there is a change in what internal energy, that means there is a change in temperature. It can be 2 temperature, θ1 and θ2, as you have studied in your junior classes. So please always keep it at the back of your mind that if temperature is increasing from T1 to T2, just like once a variable value of what temperature, we can also say the U is given by, I told you, always keep that at the back of your mind, integration of the U, changing internal energy is integration of the U, so which is the same thing as the integration of F by 2 nRT or nR dt. So please keep it at the back of your mind. Guys, when we say if the temperature of gas is increasing, this is for temperature increasing. On temperature increase from T1 to T2. So if you have this kind of case, this is what you use. So keep it in mind, you've studied this under kinetic theory of gas, so I won't talk too much on that. So the last parameter, which is work done, which is the last one. We take them one by one. The work done by gas. So work done by gas is the last parameter from the first law, work done by gas. So if we go by the work done by gas, we have two cases. So we say when work is done, we've talked about work done when we talk about the topic of our, what do we call it, viscosity and hydrodynamics. We've talked a lot about this, the Knowles principle, even wonder work, energy, and power. We've talked about this time and time again. Remember, if gas expand, important points we can write down. If gas expand, if gas expand, we say the volume increases. So we say the work done on the body is positive work is done. So the other definition you can also keep is if gas, I said it's going to be a long video, just have to keep it calm. If gas compress, though at a level I have to increase the or compress it as the case may be, volume decreases. Apology for my video camera. I told you I'll work on this as soon as possible. I don't like a situation whereby I'm not being showed. So from what we have talked about, we know that work done by the body is integration of the W. Work done is pressure times volume. So it will just be integration of P dV, taking limit from V1 to V2. So work done is always equals to P dV. So which I said we've studied. So for now, guys, I think you just need to memorize. Just we've talked about this before, time and time again. That is F is degree of freedom. And when we talk about degree of freedom, we have monoatomic gas and diatomic gas, which we have studied before. And for work done, this is what you need to keep in mind. Integration of PdV, taking the limits from what V1 to V2. And for Q, I told you NC dt, or integration of NC dt, taking the limit of temperature from T1 to T2. So these three definitions by conservation of energy that we have used to define force law, even in your chemistry, Q equals to W plus Du. It's the interpretation, the mathematical interpretation of force law. I hope all of you have to understand this, and it's very important before we move to the next slide. Now, about the next slide, we are going to talk about molar specific of a gas and thermodynamic process. So it's still going to be a lengthy video here, and you just need to follow through because derivation might be important, and formula is why we are doing all these things. The formulas are very important to keep in mind. Now, when we talk about the molar specific heat of a gas, let me just make it something interesting. You just have to follow through and you have to write that. It's very important to be a very good physics student. Now, when we talk about molar specific of a gas, we say they are not constant. So we define them in two ways, which we call the standard molar specific heat capacity. The amount of what heat required to raise n mole of the gas is called Q. So, and when we define the molar, I told you, they depends on other parameters. So those parameters are what we can say, we define the molar specific heat of a gas in two standard what way. So we can just say the standard molar specific heat, standard molar specific heat is defined in two ways. The first way is the way we call, we have a molar specific heat, molar specific heat at a constant volume. So we write that as CV. Please keep it in mind. Molar specific heat at constant volume. It is written as CV. So when we say the molar specific at constant volume, the definition we give to it for the sake of those of us we are writing examination theoretically, it's just the heat required, like I said, to raise the temperature of 1 mole of a gas, and say more or less like your specific capacity, 1 mole of a gas. It's not always easy to write, by 1 Kelvin, or you say 1 degree Celsius, anyhow, at constant volume. So the molar specific of a gas can be what? Can be at constant volume, which is the first definition we give to standard molars, specific heat capacities, if you like, or specific heat. So now, for now, I will only limit ourselves to what is required with the syllabus, on the syllabus that is available in your syllabus. I will not talk too much about a lot of things that is not required. So if we say from our first law, so let's just say using first law for the derivations, let's using first law of thermodynamics, which I've given to you. I said I'm not going to use the differential form anyhow. Change in amount of heat supplied to the body will bring about change in internal energy, which also bring about what the work is done by the body. Don't mind my W, that is looking like omega. So for now, we are going to take it one by one. So we are taking a molar specific capacity of a body at constant volume, we denote by CV. So now keep it in mind, molar specific heat can be defined under two words. Standard property. At constant volume, it's required to raise the temperature of 1 mole of the gas by 1 Kelvin at constant volume. It's called CV. So molar specific capacity at constant volume is called CV. So using this formula, we've talked about this. Q is given from formula I just talked about, not quite long. I told you, let me demarcate so that I will be able to have enough space on this platform. If I have this is going to be Q is given as a NCV, change in temperature. We'll talk about that. And the internal energy is F by 2 nR dt. As you know, there is no work done when what? The volume is constant. I told you work done by the body is what? PV, pressure times volume. So if you want to talk about the W, they say is the integration of the U, which is integration of P dV, taking the volume from V1 to V2. So if volume is constant, that means no work is done on the body. So we can now just cut out on simplification. On simplification, we can say N get cancelled out. As you can see, my dear student, the T also gets cancelled out. This should be NCV F by 2 nR dt. The T also gets cancelled out. So what we are having, guys, left here is that CV is equals to F by 2R. So this is another important formula we always want students to keep at the back of their mind. Many times I use this in classroom when I'm doing numerical questions, exam questions directly. And most of us just like, you've already mastered it. Molar specific capacity at constant volume is equals to degree of freedom divided by 2 multiplied by what? R. I hope you know what R stands for. And for now, F by 2 nRT is not going to be a problem for you because we've talked about R, molar gas constant, 8.31 times 10 to the power -4, 0.0831. Molar gas constants. We've talked about that more and more in your chemistry classes. So that is that. This is a good formula you need to keep in mind. We've talked about it. If it is a monoatomic gas, the monoatomic gas is having what? Degree of freedom is 3. You can keep it in mind if you are just joining us. For diatomic gas, diatomic, degree of freedom, atomic. I have a long way to go. I'm just thinking maybe I'm going to do this video in 2 sections. Sorry about that, but I don't want to overrush you because it's going to cause you. So CV equals to F by 2R is very important for students to keep at the back of their mind. So the second standard molar specific heat is called the molar specific heat as constant pressure. So we can also write the second one is called molar specific heat at constant pressure. So the molar specific heat at constant pressure is denoted by Cp. You can see. So that means there are two types of C. When you are considering your Q is equals to W plus the U. So that means Q equals to NCV can be CV and can be Cp. So from definition, you can just write the amount of heat required to raise temperature of 1 mole of a constant at constant pressure. So amount of heat required to raise the temperature of 1 mole of a gas by 1 Kelvin, if you like, say 1 degrees Celsius at constant pressure. So if we go by that, you can see that pressure is constant this time around. So we say using first law of thermodynamics, just like I've done that. So using first law, just like the way I've done in that place. So if we use first law, pressure is constant. FLT means first law of that thermodynamic, which is the Q equals to the U plus the W. So we know the Q is there because it is the Q, that is N. Now it is now Cp. NCP change in temperature. The U is F by 2 NR dt, just what we have there. Then work is now P dV. Remember, you also need to understand something here because it's very important if you want to derive. I have to just show this because most of your A-level question ask you to derive this. You can also say from gas law, continuation from this side, from gas law, which we know that PV is always equals to nRT, always valid. We've talked about all these things before. So the differential form of gas law differentiates this. If we differentiate, we are going to have P, you can see P dV. I'm differentiating plus V dP using your normal, what you call product rule. I know you guys should know that is equals to NR is a constant, then dt. So now if we go by this particular thing of differentiate, when you differentiate the gas law, the value you get, PdV plus VdP equals to NR dt, is called the differential form of what gas law, which you can also keep in mind for now. Differential, like I said, I will help you form of gas law to break this video into two parts so that we are not going to have issues for lengthy video. So that I'm going to call, because I still have second law of thermodynamics and exercise. So I'll break it down to two different parts for us to understand it carefully. I'm not going to rush you guys because normally I'm supposed to do it kind of 3 hours video, but I'm looking at it as if it's going to be too long. So this is differential form of gas law. And if it is differential form of gas law, from there we can substitute. Since pressure is constant, we can just write, since we are talking about molar specific heat at constant pressure. So since pressure is constant, so I think that one is very easy now. Pressure is constant, we can just cancel out the side that has pressure. dP is constant, you can see pressure is not changed, so this is 0 times V. So we can just say P dV is equals to, let me manage space because I have a lot, NR dt. I hope you understand. Pressure is constant, so dP is equals to 0. So note that. So if we have that, so we can now say if P dV equals to NR dt, equation 2. Look at my first equation. P dV is NR dt. So P dV here in this equation, I'm going to substitute NR dt. So on simplification, I'm now going to say, therefore, let's change the color. So therefore, we can say from this equation now, you can see NCP dt is equals to, I just want you guys to follow us. That is this is look at this now, F by 2nr. Look at what I did there, guys. F by 2, see, F by 2r is CV. I hope you understand. F by 2r is equals to CV from our first equation. So if F by 2r is equals to CV, so F by 2r, I will change this to CV. So I'm going to be left with N CV dt. So please keep that. So that means I can write the U as NCV dt. Students need to keep that now at the back of your mind. I told you I'm not going to rush you because this topic is very important for A-level students and for O-level students to some extent. So the first law and the parameter, how it works, you can keep it, but there is no way if you're doing physics on real level, this you are going to face. So all college students are going to need this for understanding sake, and derivation is important, and that is why I'm doing it. So plus, I told you PdV is now nr dt, so nr dt. Let's cancel out as usual. From cancellation, n gets cancelled out, as you can see. I hope students can see that dt also gets cancelled out. And what we have here, which is what you need to put, Cp is equals to Cv plus R. Cp equals to Cv plus R. So you can also say Cp minus Cv is equals to R. It's a formula which is important in this study, in this thermodynamic process, which we call this particular formula. You know, I told you whenever I ring out a formula, it's very important. It's called the Mayer's relation. Mayer's relation. A-level physics students, you keep it in mind. This is called Mayer's relation. The Mayer's relation is very, very important for you to keep in mind. So from what we see here, that means if we are subtracting Cp from Cv, we can conclude or infer that Cp is always greater than Cv. So always keep that at the back of your mind. So that means at constant pressure, some part of the heat is used in work done. You know, Joe still told us that heat can be converted to work. But in the study of gaseous system that we're talking about, which we are still going to talk about when we go to refrigeration and Carnot energy system, that is part 3. I'll talk more about that. We are going to let you know that not all heat can be converted to work. But in this case, so far we have molar specific heat at constant pressure, we call Cp, minus molar specific heat at constant volume, we call Cv, is equals to molar gas constant. And this relation we call Mayer's relation. It's telling us, we can just keep a note that, therefore, we always keep in mind that Cp is always greater than Cv. And the meaning of this is that what the work done is 0. When work done is 0, the whole heat, I hope I'm not writing on the advert, the whole heat is used, to increase temperature. So you can keep that in mind. So when the work done, but you know, work done is PdV, and when the heat is changing, integration of PdV, taking limit from V1 to V2. So what I'm saying here is that we know that Cp equals to Cv plus R. We can also conclude this is not the end of our derivation, but this particular formula is important. Like I said, it is called the Mayer's relation. So in continuation to that, let me continue from the next slide. For understanding sake, we say Cp is equals to Cv plus R. Remember? So, and we've talked about Cv just now. It is equals to F by 2R. So if I substitute, I have Cp is equals to Cv is F over 2. When I say F by 2, I mean F over 2R plus R. So in what? Concluding this, we say Cp is equals to F plus 2 over 2R. So what I'm writing here is R plus R is 2R. So that is that. So we now say Cp is equals to For monoatomic gas, I told you it is 3. So it will be equals to 5/2R. Keep it in mind. This is a monoatomic gas. And for diatomic gas, molar specific at constant pressure is given as 7, that is 5 plus 2, 7/2R. This is diatomic gas. So whereas for CV is 3/2 and 5/2 respectively. So just keep it from in mind at the back of your mind. And again, we define another important parameter under this, which I think is also important. We call gamma. That is a ratio of molar specific heat. Ratio of molar specific heat. So under this, like I said, the ratio of molar specific heat, which is gamma, is now given as Cp divided by Cv. So keep that in mind. Let me also highlight that it is also very important also. So the molar specific heat, ratio of molar specific heat is called gamma. So please, that is the interpretation we give to that. And if we do that, we can also, in terms of gamma, if you have question, you can write Cp and Cv in terms of gamma. For example, if you substitute from the formula, Cv is equals to F/2R and Cp is equals to F plus 2/2R. So please keep that at the back of your mind. So from that, we can say Cv, if I substitute without wasting time, is simply as R over gamma minus 1, and Cp is equals to gamma R over gamma minus 1. So please, if question is in terms of molar specific constant, which is the ratio of specific heat, gamma, if it is given, so this is the interpretation you give to it, and that is how it is being done. So please, guys, very important, formulas are important in physics, and that is the essence of giving you all important formula as you need them. So this is all about the standard parameters which we talk about, the heat supply, the work done, and change in internal energy, and what you need to know about the Mayer's relation, and as well as differential form of gas law, as well as what the molar specific heat, which we define under 2 parameters at constant volume and at constant pressure. So I believe you understand this. So the way we've done in our what's it called, this fine topic we call the topic of kinetic theory of gas, we talk about we can mix different gases. We can also have an equivalent mixture of specific heat. Maybe I talk about it for the sake of numerical wise. Essence of doing all these things because of your numerical. So we can have equivalent mixture. Let me just talk about it here. Equivalent mixture of specific heat. So if we talk about the equivalent mixture of specific heat, we can just talk about, from now, you all know the formula for change in internal energy is F/2 nRT. From now, we are now using, I told you, because F/2R is Cv, I can always write it as NCV/dt. So keep this change in formulas and interpretation of formula at the back of your mind. So if we have, if we are actually mixing the internal energy of a system, so we are talking about, we have N, the first one, N1, C1, T1 plus N2 plus N2, C2. Then we have T2, N1, C1, V1 plus N2, C2, V2, like that, like that, like that, like that, like that, like that. N1, C1, V1, T1. I have that, then continue like that. So we can say something like equivalent specific heat. Equivalent, that's the total amount of molar specific heat at constant volume, can be N1 C1 plus N2 C2, that is C1, CV1. When I say CV1, CV2, for understanding sake, over N1 plus N2. So when you are mixing at what? Different mixture of molar specific heat at constant volume, this is what equivalent you have. If it is for the mixture of what at constant pressure, the same thing we hold. So we can say, just let me write directly, no time, equivalence, CP equivalence. That's like the way you are equivalent capacitance and equivalent resistance. It be N1 CP1 plus N2 CP2, like that, over N1 plus N2. So it continues in that manner. So that is when you are mixing gases. When gases are mixing and their molar specific heat are changing. So the way we get the what? The equivalent molar specific heat is by N1C1, N2C2 over N1 plus. That is the way we do it. And if you want to do it in terms of gamma, it can also be in terms of gamma. You can say N1, if it's in terms of gamma, maybe I take a space to write, it can be N1 plus N2 over gamma equivalent minus 1. Like that. So whatever might be the case, I think this is just okay for you to keep in mind. N1C1 plus N2C2 is equals to N1 plus N2. So this is the way we relate the relationship between our molar specific heat when they are being mixed together. I hope students understand this. And before we go to that, we still have one more process to talk about, which is our thermodynamic process, which is the last slide for this section. In the next video, which is the second and the last video for this, I'm going to talk about thermodynamic indicator diagram or the PV diagram. So for now, I will quickly explain what is called the thermodynamic process, and understanding that, we are going to provide a new slide for that. Now, fine. About this, I'm going to talk about the thermodynamic process. So because I don't want it to be too much in one video, though most of my students believe they prefer me doing everything together in one so that they know they have learned all what is needed to know under the topic. But some of you with mail I got, you asked me to help you to reduce the duration of the video because it is kind of lengthy. So that is why I'm going to do this twice. Normally, I believe we do it once and let's face the next chapter. So we can talk about when we talk about thermodynamic processes, we just mean that we are saying any process in which a gas can be changed, the state of gas can be changed. So it is just the process of changing the state of a gas. So the process of changing the state of a gas is called what? Thermodynamic process. Like we've studied in KTG, kinetic theory of gas. We said when we define state of gas, we define state of gas in with three parameters. Remember, the pressure, the volume, and the temperature. So if we have the first, look at me, pressure I call P1, the first volume I call V1, and the first temperature. And this changes to E2, V2, and T2. You can say the pressure, the volume, and the temperature has changed. So this type of process defined, or we call a thermodynamic process. So you keep that at the back of your mind. So a process that involves the change in pressure, volume, temperature of a gaseous substance is called, so whereby the starting point here is called the initial phase, or if you like, you say the initial state of a gas. And here we call the final state of the gas. So most of these things are being taken in chemistry, where we talk about when volume is constant, when pressure is constant, when temperature is constant. So all these processes are what we want to look into. And when we consider this thermodynamic process, students need to understand that there are infinite processes. In fact, I can just write it in language, there are infinite thermodynamic process or thermodynamic processes. That is the process in which the pressure, volume, and temperature can change from one state to the other. They have infinite numbers of ways. But in physics, we are what they are only classified into two. So we classify them into two main types, which you need to understand, or two categories. We can say the first one is called polytropic process. Like I told you, I'm not going to rush you, and I'm going to do this video in two video series. Polytropic process. And when we say polytropic process, we say the molar specific heat is constant. Keep that at the back of your mind. So, and the second one is called the non-polytropic process. So as I said, I will use 1 hour for this video. 1 hour is not always enough. Non-polytropic process. So far, you don't want a 3 hour. So in this case, C is not constant. I will say C varies. So when we say C varies with what? The change of state, that is the pressure, the volume, and the temperature. So now, we categorize change in thermodynamic process into two categories: polytropic process, and for what? The second one we talk about non-polytropic process. So about the polytropic process and non-polytropic process, we are going to talk about them in details when we talk about examples of all these processes in our next video, which will be the part 2, where I'm going to finish all what we talk about when we talk about the standard polytropic process. But for understanding's sake, now the polytropic process are now divided into what we have. When the molar specific capacity is constant, they are now classified into the following, which we call the standard. I want to change to a blue to finish up the video. Standard polytropic process. That is when the molar specific heat is constant. So note that they are classified to the first process we call isochoric. They are just named. That is a isochoric process, which is also termed isometric. Please be careful because of exam. That is why I'm writing every damn thing that I believe it's important. Isometric, which is when volume is constant. Please note that. The second process we define is what we call isobaric. From the word baric, pressure is what we talk about. Isobaric process. And that means the pressure is constant. Let's note that. The third standard process we talk about is isothermal. From the word isothermal, I know most of you are used to that. Called isothermal process. Permit me, that something is hanging. Isothermal. Isothermal process. Okay, I'm back. Isothermal process. And isothermal means the temperature is constant. And the last process under standard polytropic processes is called adiabatic process. Adiabatic process. Which means the change in temperature, the Q, is equals to what? 0. So these are the standard polytropic process, which we are going to be considering one by one in our next video with respect to PV diagram, which is called the indicator diagram. And we are also going to talk about what we call the cyclic system, and as well as the second law of thermodynamics. So I will explain indicator diagram, and I will also talk about the slope of each of all these processes, which I believe I'll talk about free expansion of gas. I'll talk about efficiency of heat engine, talking about the Carnot engine system and the refrigeration. So based on that, that will be I will try as much as possible to also use an hour for that, or 1 hour, 30 minutes. This permits me, because understanding is the most important thing, and exercises are also going to be there. So I would have loved to do more, because I timed myself and started exactly 2 minutes after. So I have just 4 minutes more, which makes me stop here. And that is why I'm going to stop here. So you can just note or keep down a note just for me to just conclude this section. So on keeping down a note, you can just note this, that for polytropic process, heat supplied is given as Q is equals to NC. We told you that this is constant for polytropic T2 minus T1. Keep it at the back of your mind. But for non-polytropic process, heat supply, variable value of C, integration, is given as. We've talked about all these things. That is one thing, but we keep repeating ourselves over and over again for understanding sake. You can see the Q is given as NCDT. So then Q will now be equals to what? Integration of NC, taking the T, not the V, the T, T2 minus T1. So that's just a note I want you to keep down. I'm going to stop here. In this video, we talked about introduction to thermodynamics, and we were able to talk about not that much of a thing, the thermodynamic process. We talked about the zeroth law of thermodynamics, where we consider thermal equilibrium. We talk about the first law, we talk about conservation of energy, and so on and so forth. So I'll stop here. See you soon. Bye for now.